So this is our review for 1105, final exam. We're going to start on question 12. So I have a projectile fired 1,000 feet above the ground at a 45-degree angle. The height follows the given equation. That's correct. So we don't have to actually determine the equation. It's already given to us, where x is the distance from the base of the cliff. What is the maximum height the projectile reaches? How far is it from the cliff at that point? So if we had to draw this, so it looks something like this. And we shoot it off here, and then eventually it hits the ground. So this would be our x variable, and this would be our h variable. So since your equation has an x, and with any parabola, our goal is to always find a vertex. Like when they're asking for the minimum or maximum, what you're usually looking for is the vertex. So do you remember the vertex formula? Close. Negative b over 2i. So the x-coordinate of the vertex would be negative b over 2a. And for any quadratic, we have whatever's in front of the x squared is the a, whatever's in front of the x is the b, and our number is c. So what happens here is, and in front of the x, even though there's nothing there, technically there's always a 1 there. So if we had to do this, our vertex would be negative 1 divided by 2 times our a value, which would be negative 8 over 500 squared. And the square is just in the bottom. So if we wind up actually doing this fraction out, if you're dividing by a fraction, that's the same thing as multiplying by the reciprocal. So our answer would be 500 squared divided by 16. Now, depending on your professor, they may want that worked out into an exact number. They may not. Since our next step, we're going to be plugging the number back into the equation, you're better off leaving it in that form to start with.
Did you multiply the negative 8 into 2?
Yes, on the bottom. The 2 and the negative 8 got multiplied together, and the negative signs cancel each other out. The 500 in the bottom, since we're dividing by a fraction, just gets flipped over into the top. So for now, I'm going to leave that as is. So this would be our x value. Any questions on that?
Why did you stop there?
So far, so this is solving this part. Because when we find our vertex, we're interested in this point. Whenever you have a parabola, the minimum or maximum is going to occur at a vertex. So they're asking, what is that height, and how far away from the cliff is it at that point? So we kind of solved this backwards. First, we found how far away from the cliff it is, which would be that value. So next, to actually find what the height is at that point, we're going to have to plug into the equation. So actually, let me scroll. Good enough. So now if we actually wanted to find the height of that point, we're going to have to plug that value in. So h of 500 squared over 16 is going to equal negative 8 over 500 squared times our x value squared plus our x value plus 1,000. So if we wind up doing this, the squared, 500 squared squared would just become 500 to the fourth, and this would become 16 squared. So now we can cancel a bit. So we have -8 over 16 squared, and then 500 to the fourth divided by 500 squared just leaves you 500 squared. That we're going to leave as is for now. And then plus 1,000. Now for this is still fairly messy. Your professor would probably want a direct answer in this case. And you are allowed calculators in this class, right? Yes. I should probably just go grab a calculator myself. I'll be right back. Can I get a calculator? Did you get an answer? Yep, I got the same thing. So if you plug this into your calculator, you get 8,812.5. So that would be our height. Just want to sign in for me. So when you encounter this kind of problem on your exam, whenever you're looking at minimum or maximum of something that has an x squared in it, just always go with the vertex formula as a starting point. Any questions on that one?
So you just put down the 8 over 500 squared down?
Yes, this is from your original equation.
How do you get 500 squared?
It would be x squared. So this would be x squared. So we're squaring that value, the 500 squared over 16. If we square that, it becomes 500 to the fourth divided by 16 squared. I mean, normally in an exam, you might have worked this out to just be a number by itself. So these would just be substituted directly. Because I'm just taking that number, putting it in here, oops, and in here. What the heck? No. What was this? Over 500 squared. Yeah. Any preference for a next question? What's that? I'm going to go through all of them at some point, yeah. But for people that are time crunched, I'd rather just answer preferred questions first. Okay. So for question 9, it's asking, given the following graph, find the intervals that it's increasing, where it's decreasing, and where it's constant. So definition-wise, if you look at any point on the function, so if you had something like this, and the function was doing this. So you want to read it left to right. So if you pick a point, and then go to the right, and see what you have to do to get back to the line. If you have to go up, then it's increasing. If you have to go down, then it's decreasing. But always go to the right, and then see whether you have to go up or down to get back to the function. So in this case, if we're looking at this graph, if we start over here, and then go to the right, to get back to the graph, we have to go up. So on this part, it is increasing. Whereas in this part, if we go to the right, we have to go down to get back to the graph. Hello. Sure. Yeah. So on that part, it would be decreasing. I don't know why it's moving around. And it's doing that for this entire part, because again, if we test a point over here, we're still going down. Whereas if we get back over here, if we go to the right, then to get back to the graph, we have to go up again. So on this part, it's increasing. In terms of where it's constant, that would literally have to be a flat line. That would be constant. This graph does not exhibit that behavior anywhere. At every point, it's either going up or going down. So there are no intervals during which it's constant. So if we wanted to then formally write the solution to this, we would say it's increasing at this left piece, and it's increasing at this far right piece. So we would say it's increasing. And it's also important to identify the turning points here, which would be the peaks. So that would be over here and over here. And that occurs at -2. And this occurs at a little, no, it's a little bit off actually. Oops. Do you need more blanks? Yeah, it's fine. So this isn't actually at -2. It's roughly at around -1.7. And this is at around +1.7. So then if we're looking from where it's increasing, once it goes off the graph, you could assume that it continues that behavior permanently. So at this point, you can assume it keeps going down, and at this point, it keeps going up. So we would say it's increasing from -infinity all the way up to -1.7. And that would be unions with 1.7 to +infinity. So on this segment over here, on the left-hand side, it's increasing. And on the right-hand segment, it's also increasing. And the only parts that it's decreasing would be this middle part over here, where it's kind of rolling downhill from -1.7 to +1.7. And just notice that I didn't put square brackets anywhere. Infinity never has square brackets, but the reason the values don't have square brackets is because right at the turning points, it's neither increasing nor decreasing. You could say it's constant at those points, but technically you need the same behavior for two different values to create a trend. So it's actually only stationary right at those 2 points. They're just turning points, but they're not included in the increasing or decreasing set. Something that, an example that would have square brackets is if you had a graph that looked like this.
So if we put that -1 in front of all those changes all the time, then we'll just be able to push them all together.
So in that case, you would actually have your endpoints included in the increasing parts. So if you happen to have a piecewise graph, it could actually have square brackets. Like let's say this was -1 and 1. So you would say this is increasing from -1 to +1, square brackets included, because you have filled in endpoints including those. But once it does this kind of turning behavior like this does, these two spots are not increasing or decreasing.
So you said this negative number times that.
Any questions?
This negative times that positive makes this negative times that positive. Because it's distributing itself over the entire equation. So at this point, you only need to put them in their proper order, and then you can simplify any of them and have the same exponent.
And just so you know, this is recorded, and this is also going to be posted online, so in case you feel like you're missing some of what I'm scribbling or saying, it's available online as well. So, the last two? Sure. Oh, calculator allowed. Perfect. A population obeys the equation P of t is equal to 400 e to the 0.3 t with t in years. After how many years will the population reach 1200? Okay. So we're given a formula for population and a value we want it to reach. Because here you have two things. You have t, which is in years. And you have population, which would be this value. So it's saying that 1200 is equal to 400 e to the 0.0t, 0.3t. So when we have an exponential function and we're interested in solving it, the first thing you want to do is isolate as much of the non-exponential components as you can on the other side. So in this case, I would begin by dividing everything by 400. So 1200 over 400 gives me 3. 400 over 400 just cancels, which leaves me with e to the 0.03t. Now what I want to do is somehow bring down the 0.3t. So just like when you have addition, you subtract. When you have multiplication, you divide. They're kind of inverses of each other. What the inverse winds up being of exponentiation, whatever it is logarithms. So you have logarithms and exponents. So what we're going to do is just take the logarithm of both sides. So on the left side, we just get ln of 3, which is what you use your calculator for. It has not really a nice value. So, like I was saying, that addition and subtraction are inverses, and logarithms and exponents are inverses. When you take the logarithm of something to an exponent, they basically cancel each other out. So what you get with this is just 0.03t. So now we've gotten rid of our exponents and we just have algebra again. So if we divide both sides by 0.3, we've isolated for t. And putting this into a calculator, since it probably wants an exact answer, ln of 3 divided by 0.3 gives me about 3.66. But since it is a word problem, just don't forget to tack on units. So 3.66 years. And this reciprocal behavior works both ways. Like if you had, here we have the logarithm of e to something, but if you had e to the logarithm of something, these also cancel out. So that would also just equal x. Same thing as ln of e to the x. These cancel, and you get x back. So those are your reciprocal operations for logarithms and exponents. Just be careful, it does have to be e. This is a special value for logarithm. If it happens to not be e, then you do have to take the logarithm of whatever base it happens to be in. I think there's a follow-up question for that somewhere. As a quick example, like if you had 5 to the x, if you took the ln of this, these don't really directly cancel, but the x does pop out. You're left with x times ln of 5. So there is kind of a trailing constant factor, but the x still pops down and is no longer an exponent. Whereas if you have ln and e or log base 10, those just directly cancel each other. So if you plugged in 1200 here, P is population, which is what we're given data on. So we're trying to find T given P. Any other questions? Sure. Well, I mean on this one specifically. No? Okay. Because I was going to do the last two first. Someone requested those, so see what 30 is. How long will it take a sample of radioactive substance to decay to half its original amount if it decays according to the function that with t as in years round to the nearest hundredth? So for that, we have to do two things first. Because in the previous question, we were just given a value as our target. We were told, what if the population is 1,200? Here, we're only told, what if it's half as much as it starts with? So first, we actually have to find out how much it starts with. So we have to calculate A of 0 is our start. And to do that, we would just plug in 0. So that is equal to 400 times e to the minus 0.2 times 0. Now, something interesting happens with exponents here. 0.2 times 0, that is equal to 0. And any number to the 0 is always equal to 1, regardless of what the number is. So this entire part is just equal to 1. So if that entire part is equal to 1, then this is just equal to 400. So that's how much we start with. Then we're interested in how long does it take to get to half as much. So half of our starting value would be half of 400, so that would equal 200. So now we actually have an amount, and we're going to set it equal to our equation to find time. And from this point, the procedure is similar to the previous one, where we're going to isolate as much of the non-exponents as we can on one side, then take the logarithm of both sides to isolate the exponents and solve. So first thing, I'm going to divide everything by 400. So on this side, we get 200 over 400, which equals a half. 400 over 400 cancels, And on this side, we're just left with e to the negative 0.02t. And we want to isolate the t in the exponent, so we're going to take the logarithm of both sides. So we have that ln of 1/2 is equal to the ln of e to the minus 0.2t. And again, ln and e cancel each other, so this just becomes negative 0.2t. So then what we wind up doing is dividing through by the 0.02, and we get that t is equal to the ln of 1/2 divided by negative 0.2t. And if we put that in a calculator, divided by negative 0.2, we get 3. Let's see, what do they want us to round to? Round to the nearest hundredth. So 10's hundred, so we need 2 decimal places. So this would round to 3.47 years. Any questions on that one? Yep. We plugged in 0 for t because the question asks, how long is it going to take to reach half its original amount? So half its original amount is a specific number, but we don't know what that is. So what we want to find is the original amount. So to calculate that is this calculation. Because otherwise we don't know the original amount. The original amount is just the amount when t equals 0, by definition. Okay, and next up we have 28. Solve the following equation. This over this equals this. So before we do this one, I'm just going to briefly review some log rules. So if you have log of a times b, that's equal to log of a plus log of b. If you have log of a divided by b, that's equal to log of a minus log of b. And if you have the log of a to the b power, the b comes out and down and becomes b times log of a. So, since we have logarithms on both sides, what our goal is going to be is to kind of get everything under a common logarithm. So we see here that we have a minus sign. So we're going to apply that rule. That if we start with a subtraction, we can turn that into a division. So I'm going to rewrite that as log of 5 plus x over x plus 1 is equal to log of 6. Does that part make sense? Okay. So now since we have everything in logarithms, like our left side is just the log of some quantity, and the right side is the logarithm of some quantity, these quantities need to be equal by definition. So at this point, we can drop the logarithms and just say that 5 plus x over x plus 1 has to equal 6. And that gets rid of our logarithms. So at that point, if you have equal sign and something that resembles a fraction, you could always turn this into a fraction by just putting it over 1. Division by 1 doesn't change anything. And then we can cross multiply. So we have 5 plus x is equal to 6x plus 6. And then we'll be looking to solve, so subtract x, subtract 6, oops. And we get, come on. We get that negative 1 is equal to 5x, so x would equal negative a fifth. Make sense? Okay. Any questions? No? Number 5? Okay. Okay, let's see. If a room with perimeter 40 feet and 12-foot walls needs 10 gallons of paint, how many gallons of paint does a room with perimeter 80 and 10-foot walls need? Okay, so we have some room. So we have a length, a width, and then since it has walls, we have height. I don't know how clear this drawing is going to come out, but right. So we're told the perimeter is 40. So let's say I just unrolled this figure. Like let's say I cut it right over here. What I would wind up having is something that looks like that. Like if I unroll the walls of the room. And we're told the perimeter, which would be the length plus the width plus the length plus the width equals 40. So this plus this plus this is equal to 40. And we're told the height is equal to 12. So without really worrying about what width and length are, we just need to know the total amount because we're going to find the area inside this figure. So the area would just be the height times whatever our perimeter here is. So 12 times 40 would give us 480 square feet. So looking into this room, if we looked at just the 4 walls, we need to cover 480 feet squared. So now we're going to set up a proportion. This is going to be room 1. This is going to be room 2. This is how many gallons we use. Okay. I'm not going to rewrite that. Well, all right. That was strange. So on the top, we're going to have gallons, and on the bottom, we're going to have feet squared. And this is going to be room 1, and this is going to be room 2. So in room 1, we had 480 square feet, and we needed 10 gallons. In the other room, we want to know how many gallons we need, so let's just call that X. And we're also told that this time the perimeter is 80, but the walls are shorter, they're only 10. So same way here that we multiplied height times perimeter, we're going to multiply height times perimeter. So 80 times 10 in this case gives us 800. And as usual, when we have two fractions, we can just cross multiply. So 10 times 800 is 8,000. And that should be equal to 480x. To solve, we would divide both sides by 480. And we would get that x equals, let's see, so since you are allowed to use a calculator in this class, just plug that into your calculator, and you get that the second room needs 16 2/3 gallons to cover its surface. And the weird part of this question, like I said, is visually unrolling this room to create this kind of rectangular figure. So the individual lengths and widths don't matter. Whatever they add up to, as long as they add up to 40 in that case, 80 in the other case, multiplied by height, gives you how much wall area you need to cover with paint. And then it's just setting up this proportion. And proportions you can rotate however you want as long as you're consistent in your labeling. So I call this room 1, this room 2. I said gallons are on the top and feet squared on the bottom. But you could rotate this however you want. You could say room 2 is here, room 1 is here, this is gallons, feet squared. As long as you're consistent, the cross multiplication is going to result in the exact same numbers. Any questions? No? And you wanted to do 26? No. Okay. Do you have to go? Like I said, it's going to be online anyway if you want to check that out. There's a link at the front desk if you want to grab it. Okay. Okay, so similar to the previous one, I think 27, I don't remember where it was, we had a couple of rules for logarithms. So in this case, I'm going to use the same rules. We just have a couple of things happening here. First, our base is not base 10, so that's one more rule I'll introduce. We have a multiplication on top with exponents, a division, and a denominator with exponents as well. So first, I'll break this up using the log A over B rule. So doing that, this division becomes log base 3 of 9 times the 6th root of x minus the log base 3 of y cubed. Then for the next step, I'm going to apply the multiplication one here and the exponent rule one there. So whenever you have a multiplication, that gets transformed into additions. So we have log base 3 of 9 plus the 6th root of x And for this, I'm going to use the log power rule. So log of a to the b, the power just comes out and down. So this becomes minus 3 log base 3 of y. And here, I'm not going to use a log rule specifically, but if you have something that says the a root of x to the b, you could rewrite that as x to the b over a. So in this case, there's no number here, but implicitly we can add a 1. Raising something to the first power doesn't really change it. So I'm going to rewrite this as log of x to the 1 over 6. Oh, and this should still be base 3. We're going to get to the 3's later as our last step to convert it. But for now, we'll just leave it like that. Come on. So using our previous power rule, since this is an exponent, it'll also come down. So we'll have plus 1 over 6 log base 3x minus 3 log base 3y. Now this log of 3 to the log of 9 in base 3, the rules of logarithm, this we can just say is equal to 2. Because for logarithms, we have that log of a of b is equal to c is the same statement as saying a to the c is equal to b. So those are equivalent statements. So what log base 3 of 9 is saying is 3 raised to what power is equal to 9? So we have this question. 3 raised to what power is equal to 9? And we know since 3 squared is equal to 9, that we could resolve that as just 2. And then the final thing we have to do, depending on whether your professor wants you to or not, is that if you have this base 3, so if you have a logarithm in some unknown base, you can convert that to base 10 by saying the log in base 10 of x divided by the log of base 10 of whatever the former base is. So this gets scaled by a division of whatever that base is in log 10. And usually log base 10, we just drop the 10. It's implied that it's there. So as a final step, we would rewrite this as 2 plus log of x over 6 times log of 3 minus 3 log y over log 3. And all of these are, in theory, base 10, but by standard, we're just dropping the 10. It's implied that it's there. So now we've rewritten this logarithm entirely as base as we can in log 10. Actually, for this one, let's just put them in. So this is log 10, this is log 10, this is log 10, this is base 10. It's preference in terms of which your professor wants you to do. By convention, you don't have to. If you want to explicitly show that you're changing base from log 3 to log 10, you may want to put those in. Any questions about that one? All right. Which one would you like to do next? Okay. Find the domain of the following function. All right. So whenever you're finding domain, the problem is asking you what values of x are safe to put in. Like you can put them in, you can plug them into a calculator, and the calculator is going to give you a number back. So for this course, you have two common problems. You have fractions or square roots. In this case, you happen to have both. So with a fraction, like if you have a over b, b can't equal 0. That creates a problem. You can't divide by 0. And for a square root, b has to be greater than or equal to 0. You can't take the square root of a negative number. So here we have two things. We have a square root on the bottom. So we know that 27 minus x, we don't want it to equal to 0 because it's the denominator. But also, since it's a square root, we know that we want 27 minus x greater than or equal to 0. So we could actually combine these. Normally, you'd calculate these two separately, see what kind of restrictions that gives you, see what kind of restrictions these give you. But here, this has an equal sign with it, but we don't want it to be equal. So we could just unify this by saying that we want 27 minus x to be strictly greater than 0. Because from the square root, it could be equal to 0, that's fine. But if it's equal to 0 and we're doing this division, that causes a problem. So in terms of the algebra of that, not too bad. We add x on both sides. And we find that we want x to be strictly less than 27. So as long as you put in a number that's smaller than 27, you'll have no issues there. And if you wanted to write that in various notations, you can start anywhere from negative infinity up to 27, but not including. Or you want the set of all x such that x is less than 27. So either of those represent your domain. I don't know if your professor prefers you answer questions like this in set notation or interval notation, but the core of it is as long as x is less than 27, then you won't have issues of dividing by 0 or trying to take a negative square root. In future classes, you'll have other functions that have further domain restrictions, but for this class, your only concern is fractions. Make sure the bottom is not equal to 0, and square roots, make sure the inside is greater than 0.
I know that we wrote 27. So the number is right there, 27. So if it says 27, why are we calling why are we trying to number?
So once we move x on both sides, what this is saying algebraically is that x is less than 27 in terms of what this is saying. Maybe it kind of looks weird that way. If that's more convenient and yeah. Okay. Any other questions? Solve the inequality and express in interval and set notation. It's a quick way to do this. So usually when you have any type of inequality, what you want to do is solve for where it's equal to 0, see where your equation is broken up either by zeros or vertical asymptotes, and then kind of point test. There's not really a quick way with all these levels of multiplications to solve this directly. So we're going to do that. So first step is setting it equal to 0 and finding your zeros. This function, since it has no divisions or fractions, has no asymptotes. So we're just solving for it's equal to 0. So if we were going to factor this, both of these numbers are divisible by 3, so we can take out a 3. They both have at least x squareds. That has an x cubed, so we can take that out. So we'll take out a 3. We're going to take out an x squared. And then once we're factoring 3x squared out of each of these, this is just a 5 minus 3x. So that's our minimally factored form of the above expression. And looking at this, if we're trying to solve it, the 3 doesn't really contribute anything, so we can ignore it. If we solve x squared equal to 0, we just get that x has to equal 0. There's no other numbers that satisfy that. If we solve 5 minus 3x equals 0, if we move the 3x over and divide by 3, so we have 5 is equal to 3x. We find that x is equal to 5 over 3. So now we're going to draw a number line. That's 0. That's 5 over 3. So looking back at our original equation, this is strictly greater than. It doesn't have an equal component. So since we solved for equal, these have to be open markers. They're not part of our solution set. If you plug those numbers into there, you would get 0, whereas we're looking for where it's strictly greater than 0. So then what you wind up doing is testing points. So usually pick the smallest numbers you can. I'm going to pick -1, +1, and what would be easy? Not much, 3. So then if we plug back in either to our original equation or our factored equation, it doesn't really matter. We don't have to actually find what the values are because all we care about are the signs. So if we put -1, we're going to ignore the 3 because it's positive, so it doesn't really add anything. We can put it here for consistency, but it won't change anything. So -1 squared would be positive. 5 minus 3 times -1. So -1 times -3 is positive. Positive plus positive winds up being a positive. So positive times positive times positive gets us a positive number. And since we're looking for greater than 0, we are looking for positive numbers, so we know at least this part is part of our solution. Then we plug in 1. 1 squared, also positive. If we plug in +1 here, that becomes -3. 5 minus 3, though, is still a positive number. That's weird, that's continuous. Positive, positive. Okay. And then for our last part, if you put in 3, 3 squared is 9. Oh, positive, 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 all multiplied together, still give me a positive number. If you plug in 3, 3 squared would still be positive. 3 times negative 3 would be negative 9. 5 minus 9 would be a negative number. So a positive times a negative gives me a negative. So that's not part of my solution. This is part of my solution. And it feels like I screwed something up because that doesn't make sense. Usually you'll have alternating regions, that's all. But it may very well just touch right at those 2 points. So, zoom standard. What? No, that is correct. So since in this class you do have graphing calculators as well, if you wound up graphing this, just putting that straight into a calculator, you get a graph that looks like this. So that would be 0. That would be 5 over 3. So looking at the parts that are above 0, that does actually correspond to that it just touches and crosses at those points. So those points are not included, but everything above that is perfectly fine, and to the left is perfectly fine as well. But now if you wanted to express your solution, so in interval notation, we would start just reading the graph left to right. We would start at negative infinity, go up to 0, but rounded brace because we're not including 0, it's an open circle, and then unioned from 0 to 5 over 3, and again, rounded brace. They're all rounded because they're open because we're strictly looking for greater than. If you were going to write this in interval notation, we would say it is x such that x is less than 0 or 0 x 5 over 3. It's personal preference of your professor how wordy those statements should be, but that does accurately express our interval notation as well. And when you are doing this, it's kind of a little bit of a shortcut if you're doing this manually, since you don't necessarily care about the individual values. You're just going to multiply a whole bunch of positive and negatives, and you care whether it's positive or negative. So while you can write down and get the exact numbers in each of your test points, all you really care about is the signs. If that's kind of weird and confusing, just ignore that and literally just take this number, plug it in either this or this equation, and see whether you get a positive or negative number. Any questions on that one? Nope. Solve by completing the square. Okay. So whenever you're doing completing the square, what you want to do is accumulate your x's and x squareds on one side and all your numbers on the other. So in this case, I'm going to take the negative 4 and move it to the other side. So that leaves me with x squared minus 7x is equal to 4. Then what we want to do is we want to take the number next to the x. See what's the easiest way to write this? Call this p. You want to add b over 2 squared. So I'm not going to factor that or calculate it. I'm just going to leave it as is. So I'm going to say I'm going to add negative 7 over 2 squared. And algebraically, whatever you do to one side, you have to do to the other. So I'm also going to add negative 7 over 2 squared here. Because what this allows you to do, once you have it in this form, you could rewrite this as x minus b over 2 squared. They'll be equivalent at that point. So then I could rewrite it as x minus 7 over 2 squared. And that'll be equal to, well, I guess we do have to calculate that. So we have 4 over 1 plus 49 over 4. So if we put that over common factors, we have 16 over 4 plus 49 over 4, which makes this equal to 50. Doesn't turn out to be a nice number. All right, well, that's what it is, though. Algebraically, that's what our number turns out to be. So what we can do at this point is we have a number on the right side and something squared. So what I'm going to wind up doing is just taking the square root of this entire thing. So a square and a square root cancel each other out. So we're left with x minus 7 over 2 is equal to, and don't forget square roots have two roots, plus and minus roots. So we have 65 over 4. How do they keep doing that? Come on. So now our next step would just be moving the 7 over 2 to the other side. So we get that x would be equal to 7 over 2 plus minus. Don't forget that. That is important. Square root of 65 over 4. Now we can do one further simplification, because if you have the square root of a over b, that's equal to the square root of a over the square root of b. Doing square roots and divisions or multiplications are commutative. You could do one before the other. It doesn't really change anything. So what we know here is the square root of 4. Square root of 4 would be 2. So we have that x is equal to 7 over 2 plus or minus square root of 65. We're still just going to leave over 2. So now these have the same denominators, so we could rewrite this as 7 plus or minus the square root of 65 over 2. And 65, since that equals 13 times 5, there is nothing we can really do. There's no factors we can take out. So this winds up being our answer. The thing to really remember is this part. There's always a plus and minus root. And this you could apply for any quadratic. If you're starting with something x squared and x in the number, move the number over, add b squared over 2, use this formula to rewrite it as a square, do this, and you'll get that. It's the same place the quadratic formula comes from, where you apply the quadratic formula directly, a, b, and c. This is kind of doing the quadratic formula step by step, slightly different method called completing the square. Any questions on that one? Okay. Graph the following function as a solid line and its inverse as a dashed line. Does your class cover translations? Yes. Okay. So we have 2x cubed minus 16. So if we look at the graph of x cubed by itself, we're going to get something like this. That's just what the base graph of it looks like. But then we have two things happening. We have vertical scaling by a factor of 2, and we have a vertical shift. Vertical scaling, vertical shift. Why do they abbreviate these? Vertical move. Down of minus 16. So what winds up happening is this graph starts rising twice as fast as it normally would. So 2x cubed would look something like this. It would just be sharper. So if this is x cubed, this is 2x cubed. And then what the minus 16 does is it just takes this and brings it down minus 16. So we wind up with something. This would be minus 16. And if we wanted to solve for roots, just to make this graph a little more accurate, we could say 2x cubed minus 16 equals 0. If we move the 16 over, we get 2x cubed is equal to 16. Divide by 2, we get x cubed equals 8. And we can actually take the cube root of this, and we get 2. Because 2 times 2 times 2 gives us 8. So we know that this crosses at 2. So now we're asked to draw its inverse as a dashed line. So by rule, whatever you have as a function, if you want to draw its inverse, you'll reflect it over the line y equals x. That's going to be dashed as well. Let's just draw it blue. So we had to reflect that. Whatever happens in the x now happens in the y. Whatever happened in the y happens in the x. So if we had a crossing here of 2, now we're going to have a crossing here of 2. If we had a crossing here of negative 16 reflected over this line, then we're going to have a crossing here at negative 16. And it's just a matter of reflecting. These are a little bit hard to draw. So oh, dashed lines. Well, I didn't draw a dashed line, but that should have been a dashed line. But basically, you should look at every single point that's on this graph, draw a line connecting it to y equals x, and it should have a mirror point on the other side. So right where it crosses, they should definitely cross. But everywhere else, they should be fairly equidistant. So if we look at this point, and we look at this point, fairly similar, and same thing at that. So without actually calculating the inverse, it lets us graphically draw the inverse just by reflecting it over y equals x. And if we did want to calculate the inverse, in case your professor says to calculate it versus drawing it, if we started with, so I'm not going to call this f of x at this point, I'm just going to call it y. You have 2x cubed minus 16. When you're doing the inverse, just like we flipped x and y in the graph, you're going to flip x and y again. So wherever you see an x, you're going to put a y. Wherever you see a y, you're going to put an x. So the inverse would be x equals 2y cubed minus 16. So if we were going to solve that algebraically, we'd move the 16 over. So we'd have x plus 16. We have a 2, so we divide by 2. And then we have a cube, so we would take the cube root. Or more accurately, f of x inverse of x. Now, your professor may not ask you to do that algebraically, but that's basically what happens. Everywhere you see an x, replace it with a y versus x. That's why back on the top, we also did something similar with replacing x's and y's. This was an x coordinate, it became a y coordinate. This was a y coordinate, it became an x coordinate, and the graph moved through those points. Any questions? No? A factory finds it has revenue as a function of price given the following equation. R is equal to negative 4p squared plus 100p. What is the maximum revenue the factory has, and at what price does it occur? So similar to, I think, maybe it was the next one actually, we have something with a squared, in this case, p squared. And it's asking for maximum, could ask for minimum. As soon as we see a squared, we're going to calculate the vertex. And now it's asking for maximum revenue and maximum price. So similar to the next one, we're also going to kind of calculate this backwards. We're going to find the maximum price, plug it back in to get us maximum revenue. So if we were trying to find the vertex, that's always going to be equal to negative b over 2a. In this case, b is equal to 100, so this would be negative 100. A is equal to negative 4, so 2 times negative 4. So that gets us negative 100 divided by negative 8. I think that's correct. And always be careful with units. So we found the vertex, which is always your variable in your equation. So this should be a price. So that is the maximum price. But now if we want to find revenue as a function of price, we're going to plug that value back in. So we're going to plug in R of 12.5. Easy way to do that. I'm going to say 25 over 2 should be the same number. So that equals 12.5. So then if we wind up plugging that in, we get negative 4 times 25 over 2 squared plus 100 times 25 over 2. It just does not like doing this. So if we square that, we get 25 squared on top. 2 times 2 is equal to 4. This we have 100 over 2, so that's equal to 50 times 25. The 4 and the negative 4 cancel. At this point, though, you probably put it into a calculator. So we have negative 25 squared, and just be careful, it's 25 squared, then the negative of that, plus 50 times 25. And that gets us a maximum revenue of 625. So that's equal to R, and that occurs at a p-value of 12.5. Any questions on that? No. 21? All right. Solve the equation. Okay, so we have a whole bunch of exponents and stuff to different powers. So what we want to do here is rewrite this in a common power if we can. So looking at the numbers, we have 16 and 64, which isn't bad because we know 4 times 16 gives us 64, and 4 times 4 gives us 16. So I know that 16 equals 4 squared. 64 equals 4 cubed. So I'm just going to do those replacements for now. So wherever I see a 16, I'm going to write 4 squared to the 3x. And then 64 is going to be 4 cubed to the 4 minus x. And this is equal to 1 over 4 squared. Now, when you have exponents raised to exponents, you can multiply them together. So I'm going to rewrite this as 4 to the 6x times 4 to the 12 minus 3x is equal to, and whenever you have a fractional power, if you want to bring this up, you have to do the negative exponent. So this will be equal to 4 to the negative 2. Now, when you're multiplying two numbers together that have the same base, these both have 4s, you're adding the exponents. So if you have a to the x to the a to the b, that'll be equal to x to the a times b. But if you have x to the a times x to the b, that would be equal to x to the a plus b. So this rule we applied here. This rule we're going to apply here. Okay. It is on HDMI. Well, it says searching all sources. Sure, whatever. So everything has a base of 4, so we're going to add these together. The 12 just stays. There's nothing for it to combine with. You have 6x minus 3x, so that becomes plus 3x, and that is equal to 4 to the minus 2. So now we have something on the left side, 4, 2 something, something on the right side, 4, 2 something. Since they're both the same bases, these two things have to equal each other as well. So then we can just write that 12 plus 3x should equal negative 2. And I'm going to move the 12 to the other side, so I'm going to be left with 3x is equal to 10, which tells me that x has to equal 10 over 3. This kind of trick you'll be using fairly frequently, where if you have stuff to the same bases, no matter what you're raising the exponents to, if they're equal to each other, the exponents have to be equal to each other. I think we had a previous question where we had the log of two things that have the same base. If those are also equal to each other, then those should be equal to each other, the interior components. So same kind of trick. And it only worked because of this. If we couldn't have done that to put them all under the same base, then you would just have to take logarithms and see what happens, which we can also do if you'd like, as a more general solution. So a more general solution to this would just to be take the logarithm of everything. Whoops, that should not be there. Oh, 64, 4 minus x is equal to 1 over 16. So if we take the logarithm of everything, the log of multiplications becomes addition. The log of exponents becomes multiplication in front. So I would rewrite this as 3x log 16 plus 4 minus x log of 64 is equal to the log of 1 over 16. Then you would just have to actually calculate those out on your calculator. So you'd physically type in log of 16. It would give you some kind of number, log of 64 and log of 16. It's a bit more messy, but it arrives at the same solution. Or, well, no, we're saying like there's no common basis. Because what you could do is say like log of 4. But then let's just say these weren't common at all. You just have to put these in a calculator at this point, and this would just be a number, this would be a number, that would be a number. So this is now then reduced to algebra. It's just a calculator. That, and that. And it'll let you solve for x at that point. Seeing that you could reduce it to common bases, though, lets you do it without a calculator. Okay. Log base 4 of some expression is equal to 2. So in this one, I'm going to start off by applying our other rule, that log of A of B equals C is the same thing as A to the C equals B. So I'm going to take this is A, this is C, and what we have here is B. So what I'm saying is that 4 to the 2 has to equal x squared minus 6x. These are just alternate forms. So I haven't actually done anything yet. I've just rewritten it in a more useful way without logarithms at all. So 4 squared I know is equal to 16. And then to solve this, I'm going to move the 16 to the other side. So I'm going to have 0 is equal to x squared minus 6x minus 16. So now I've taken this logarithm problem and reduced it to solving a quadratic. So to solve a quadratic, we take our a and c. So we have a 1 here implicitly. So 1 times negative 16 is just equal to negative 16. And we see what can we do to make negative 16. So we have 1 and 16, 2 and 8, 4 and 4, and that's about it. But we have to find a way to get to negative 6. So I would do positive 2 minus 8. So I'm going to say that 0 is equal to x squared plus 2x minus 8x minus 16. And this should still equal that. Now I'm going to factor. So take an x out, x plus 2. And then if this method works, copy this over on here. And we want to see, can we get from x plus 2 to minus 8x plus minus 16 somehow? And we can by multiplying by minus 8. So then our factors would be whatever's in the parentheses and whatever is outside the parentheses. But now to solve, remember we're setting them equal to 0. So x plus 2 equals 0 and x minus 8 equals 0. That's telling us that x has to equal 2, negative 2, and positive 8. And I mean, from here onward, this should be material you've learned in a previous class. The important part is this top part, remembering this rule of what logarithm means. So while it looks weird, all it's saying is that in a different way. So we took those numbers and just kind of reformulated what we're trying to say with the log definition. Okay, solve the equation. So e to the x minus 2 is equal to 4. This one would be a calculator one if your professor wants a direct answer. If not, then we would just go back to our rules of lins and exponents that ln of e to the x cancels those, and e to the ln x, those cancel. So if we're trying to isolate the x on top, what we're going to wind up doing is just taking the ln of everything. So if we take the ln of that, these cancel. We're left with x minus 2 on this side, and that will be equal to the ln of 4. And to solve that, we would add 2 on both sides, and we arrive at x is equal to ln of 4 plus 2. If your professor is interested in a specific numeric answer, that gets plugged into a calculator. There is no quick and easy way to numerically figure out what the ln of 4 is. So usually on an exam, I would say this is sufficient. Because putting that into a calculator and actually getting a decimal number, some weird looking decimal number, doesn't really help any kind of understanding of what's going on. Because if you did plug this in, you would get 3.3863 ... It just keeps going. So depending on your professor, they may prefer the formal answer, they may prefer a decimal answer. For me, the formal answer conveys a little bit more meaning about what's going on in the original expression. If you only have decimal answers on a multiple choice exam or something like that, you'll have that. Are you all in the same class, by the way? So curiosity? No? Okay. I don't know how many sections of this class we have, so. Okay. Yeah. Okay, but you don't? No. Okay. His exam will be similar. Which one?
27.
27. Calculate the following logarithm using a calculator. Okay. So this one pretty much just relies on using your calculator, and we'll just be using this rule that the log of AB is equal to the log base 10 of B divided by the log base 10 of A. Because this we don't have in a calculator. Not in calculator. But this we do in calculator. So log base 10 will just be your standard log button. So we would say that log base 4 of 11.5 would be equal to the log of 11.5 divided by the log of 4. And since it says calculate, that usually means till you get an answer. So if you did put that into a calculator, log of 11.5 divided by log of 4, 1.76178 ... Just keeps going. But what you can also do is you don't necessarily have to use log. All that matters is that the bases on the top and bottom match. So you could also rewrite this in terms of natural log. So whether you press natural log on your calculator or the actual base 10 logarithm, they both result in the same number. What you can't do is mix and match. You can't do log of 11.5 and ln of 4. They have to just be consistent. But as long as they are, they'll all be equal to the same numbers regardless of what base you're in. You going? Okay. You're welcome. Like I said, if you're interested in the rest of it, it'll be posted online. So I should probably get another copy of that. Can you go tell Deanna? Yeah. Tell her that, just to print it off the tiny CC link. She should know what I'm talking about. Just the final for the previous year. Yeah. Have a good day. When is your final, by the way? So curious.
Monday.
Ooh, okay.
Yeah.
So soon. So I got to actually like clean this up and put the video up soon. Okay.
We have until, I have until 4 because I have time.
Okay. But yeah, I was just wondering if I can just. Yeah, we're gonna print out a couple. So. Do you have any more specific questions, or just want me to start doing them in order?
We can just do them in order instead.
It's up to you. I mean, you're only here till 4, and I'm doing this till, I don't know how long, whenever I'm done. So it's up to you if you just want to ask me specific questions.
Maybe go ahead.
Start doing them in order. Okay. So we did 1. So we'll do 2. Solving the inequality. So, similar to what we did in a previous question, whenever you're solving an inequality, you can't really directly solve it. You want to find where your zeros are and your discontinuities to create a number line and proceed from there. And then you'll wind up doing test points. So, in this case, we have, if we're solving this for 0, we have that the absolute value of 2 minus 5x equals 4. Now, what the absolute value means is that it branches out into 2 possibilities, a positive possibility and a negative possibility. So we have 2 minus 5x equals 4, and 2 minus 5x equals negative 4. So we have a positive and a negative version, and now we've gotten rid of the absolute value signs. So next step is to solve them. So we'll add 2. No, we'll subtract 2. So that gives us that negative 5x is equal to 2, and negative 5x is equal to negative 6. And then we'll divide by negative 5 on both sides. So that gets us an x of negative 2 over 5 and an x of 6 over 5. Okay. So then we'll draw a number line. We have negative 2 over 5 and 6 over 5. And I just need the original equation. There we go. So the original equation has you looking for strictly greater than. So if it's strictly greater than, these will be open points. So these will be open, open. So our next step is to find test points. The easier the better. So I'm going to use 0, negative 1, and positive 2. So if we evaluate that for each of those, the absolute value of 2 minus 5x for negative 1, 0, and positive 2. So if we plug in negative 1, negative 5 times negative 1 is positive 5. 2 plus 5 is 7. So we have the absolute value of positive 7, which equals 7. If we plug in 0, 0 would be 2 minus 0, which gives us 2. Absolute value of 2 is equal to 2. All printed? Cool. Yeah. Sure, we'll have extra. We've had people come and go. Not yet, somehow. The sun is still kind of high because of the daylight saving. Oh.
Can you guys see if you read it, or you want to write down the slide?
So then if we plug in 2, interesting. I think this one actually might be a trick question. So if we plug in 2, 2 times 5 is negative 10. 2 minus 10 is negative 8. But the absolute value would be positive 8. So we find that in this region we're positive, in this region we're positive, and in this region we're positive. why would that be? -2/5. Oh, whoops. I forgot to write down our test condition. So we're testing for which regions are greater than 4. So is 7 greater than 4? Yes. Is 8 greater than 4? Yes. Is 2 greater than 4? No. So our solution sets are actually this region and this region. So our middle region is actually not part of our solution set. So yeah, that's a good point, that always make sure you're evaluating against the correct conditions. Over here, I had assumed we were just looking for greater than 0. We're not. Actually, at this point, we're looking for greater than 4. So if we were going to describe these regions with set and interval notation, this would start at -infinity, go up to -2/5. And again, since we have an open circle, this would be a rounded parentheses, and we would union it with something that starts at 6/5. And again, since it's an open circle, rounded parentheses, and goes off to infinity. And in set builder notation, we have x such that x is less than -2/5. That's representing the left side, or x is greater than 6/5. Representing our right side. Any questions on that? Nope. Okay. So find the distance between 2 points. So this would be a formula. Call this point x1, comma y1, and call this point x2, comma y2. So for any 2 points, if we're calculating the distance, it's always going to be equal to the square root of differences in y's and differences in x's squared. So we'll have y2 minus y1 squared plus x2 minus x1 squared. So does your professor have like a formula sheet, or just have to remember all of these?
Remember it.
Okay. So this question basically comes down to whether you remember this formula or not, because after this, it's just plugging in numbers and doing calculations. So if you remember this formula, we'll start plugging in numbers. So y2 is equal to 7, y1 is equal to 2 squared, plus x2 is equal to 3. And just be careful with the subtracting negatives. So here we have minus -5, which eventually will become a positive. So 7 minus 2 is 5, so this becomes 5 squared, plus 3 minus minus 5, this minus minus becomes a plus. So 3 plus 5 is actually equal to 8 squared. So this becomes 25 plus 64, which is equal to the square root of 89, which I don't think anything factors that nicely. Nope. So this is our answer. And the way to check that is to find the closest, like let's say you do want to make sure this is actually factored, this is something your professor cares about. You don't have to check that many numbers to see whether that is factorable if you have a calculator, because all you have to do is check up to the closest root. So the closest square. So the closest square to this would be 100. So, and the square root of 100 would be 10. But this is smaller than that, so all we have to do, if you list the numbers, is check whether it's divisible by those 9 numbers. But we don't actually check all of them, because clearly it's divisible by 1, but that doesn't help us. If it was divisible by 2, this should be an even number, but 9 is not an even number. So if it's not divisible by 2, it's actually not divisible by 2, 4, 6, or 8. So at that point, all we're left to check is whether this is divisible by 3, 5, 7, or 9. But again, if it's not divisible by 3, it's probably not divisible by 9. So 4 quick divisions on a calculator, they all resulted in numbers with decimals, which means this is basically what we're left with. Again, that's only if your professor absolutely is picky about super simplification. If not, maybe put that in a calculator, get a decimal answer. Yeah. So any questions about that? Just comes down to remembering that formula. If you remember it, you got this question. If you don't, it's not much. Yeah. Determine algebraically whether the equation is symmetric with respect to the x-axis, y-axis, and/or origin. Okay. So symmetry. We have a couple of different types. We have x symmetry, we have y symmetry, and we have origin symmetry. Origin. So if something is x-symmetric, then it's reflected over the x-axis. So if you have a function that does something like this, and if it's symmetric, actually wouldn't be x-symmetric what I'm talking about. That would just be its inverse is symmetric. Let's take that labeling off too. Let's start with y-axis symmetry. Y-axis symmetry is a little bit easier. So if you look at this figure, anything that's happening on this side is also happening on this side. So it's kind of like a mirror around the y-axis. And the way you would test for that is given f of x, if you plug in f of negative x, they should result in the same values. For x-axis symmetry, what would that look like for a function? Okay, so for x-axis symmetry, we're going to have a figure that if you look over the x-axis, what's happening up here is mirrored down here. And the way we test that algebraically is if we have that f of x is also equal to negative f of x. So that if you have a solution here, there's a solution going up, there's a solution going down. In that case, you'll have a graph that is x-axis symmetric. So now we get to the last one, which is origin symmetric. So origin symmetric is a little bit tricky, but it's basically saying that we're not going to look just over the x-axis or the y-axis, but kind of through the origin. And a classic example for origin symmetry is x cubed. Because x cubed does something that looks like this. And what you're trying to do for origin symmetry is, if you pick a point, go a certain distance into the origin, keep going on that line that same distance, it should land back on your graph. So if it does that, then it's symmetric through the origin. And origin symmetry would be that whatever value we have here in x and y, they have to pair up to a negative x and a negative y value. So f of x should be equal to negative f of negative x. So whatever the value is on the right side, if we're going up, if we look at the mirror point on the left side, we should wind up going down. So then it's just a matter of plugging in and seeing what happens. You could graph it. If you graph this, you kind of know immediately whether it flips over x, whether it flips over y, or whether it does this kind of weird origin symmetry. But it says to determine it algebraically, so that is what we're going to do. So for this, we have f of x is negative 3x cubed plus 4x. And is that equal to the negative of f of x? Let's put a question mark there because we don't know. So if we distribute the negative, we get 3x cubed minus 4x. So if we look at those algebraically, negative 3x cubed plus 4x. Are these the same thing on both sides of the equal sign? And they're not. Here we have a negative 3x cubed. Here we have a positive 3x cubed. We have a plus 4x and a minus 4x. So this does not work. So it is not x-axis symmetric. So the next thing we're going to try is origin symmetry. No, y-axis symmetry. So we have negative 3x cubed plus 4x. And then question mark, is that equal to? And what this symbol means is that everywhere you see an x, replace it with a negative x. So negative 3 negative x cubed plus 4 times negative x. So if you have a negative, why does it keep falling asleep? I'm writing on it. If you have a negative squared is a positive, but a negative cubed is still a negative. So negative x cubed actually winds up being positive x. Positive x times negative 3 gives you negative 3x cubed. So this is looking good so far. We have a negative 3x cubed, negative 3x cubed. But this multiplication gives you a negative 4x. So on this side we have a positive 4x, there we have a negative 4x. So this also does not work. This is not x-axis nor y-axis symmetric. So then we're going to try whether it is origin symmetric. For origin symmetric, we need f of negative x, which we have already. So f of negative x is this. And if we negate those, so negative 3x cubed plus 4x, that we can just get from here. And if we negate all of these, we get 3x cubed plus 4x. So now our 4x's match, but now these don't match. So this is also not origin symmetric. So it is not symmetric in any of our standard respects. And if you wound up graphing this, which on your exam you can do, is verification for x, you get a graph that looks like this. That's weird. So for origin symmetry, we're going to define origin symmetry as negative f of x is equal to f of negative x, which, looking at our y-axis symmetry, we already have defined those quantities, and the x-axis symmetry. So finding negative f of x for the x-axis symmetry, this would be equal to 3x cubed minus 4x. Getting f of negative x from y-axis symmetry calculation, this would be 3x cubed minus 4x. And if we just take a look at whether those two values are equal, they are indeed equal. So while this graph does not experience x-axis nor y-axis symmetry, it does experience origin symmetry. And if we actually look at the graph, we do see that it is not reflected over the x-axis, it is not reflected over the y-axis, but it does experience origin symmetry if you do look closely at how it's reflected through the origin. So, any questions? Functional mathematical way to do this by yourself. Like there's no process that says do this, do that, and you'll get an answer. So it's just kind of looking at the equations and seeing what you can do.
Kind of like that, right? You gotta keep playing until you get to the end.
Pretty much, yeah.
The ones you haven't done.
Okay. Let's see. Oh. Okay, so for this, we are substituting f of h into a function. So basically what that means is everywhere that we see an x, we're going to substitute for an x plus h. So we have a 3x squared, so we're going to do 3x plus h squared plus 2 times x plus h minus 4. So if we square this out, we're going to get x squared plus 2xh plus h squared plus 2x plus h, that stays the same for now, minus 4. And then we're going to distribute. So we're going to get 3x squared plus 6xh plus 3h squared. And then the other factors, the 2xh, we're going to get plus 2x plus 2h minus 4. So then we try to see if we can do any simplifications. The only real simplifications we can do are if the terms have the same exponents. And here we have a mix of x's, h's, xh's, x squareds, and h squareds. So there's nothing we can actually additively combine. So that will be our final simplified answer. Did 7, 8. Given the function, list the x-intercepts, if any. So whenever we're trying to find x-intercepts, what we're really doing is setting y equal to 0. Because if we have this, anything that occurs on this line, y is equal to 0. Anything that occurs on this line, x is equal to 0. So for x-intercepts, we're looking for that. So we're going to set this entire equation equal to 0. x minus 3. So then if we cross multiply, we get 0. Because 0 times x minus 3 is still 0, is equal to x squared plus 4x minus 21. Then if we do our AC factoring, we need to find two numbers that multiply to negative 21 and add up to positive 4. So in that case, we have x plus 7 and x minus 3, giving us x values of negative 7 and positive 3. Now, formally, since this is asking for x-intercepts should be coordinates. So your answer is actually negative 7, 0 as a point, and positive 3, 0 as a point. Uh, 9 I did, increasing, decreasing. So you're trying to fence a garden with 30 feet of fencing. If the length of the garden is x feet, express the area as a of x as a function of x. So any garden is going to be some kind of square. Whoops. Perfect rectangle. So even though it doesn't say this is a rectangle, we're going to assume it is a rectangle. So we have a length and a width. And functionally, we're told that there's 30 feet of fencing. So that would be equal to the perimeter, because we're going to go around and have 30 feet of fencing. We also know the perimeter happens to be equal to 2 lengths plus 2 widths. So if we set that equal to 30, if we divide everything by 2, we get L plus W equals 15. And you'll see why I'm doing this shortly. I'm going to move the W to the other side. So I know that L is equal to W is equal to 15 minus W. So that gives us a relationship between length and width. But what this question is really asking for is area. And we are told that the length is equal to x. Let's see. So if we do our substitutions here, we know that x is equal to 15 minus w. So actually, I moved this around incorrectly. If we move this around the other way, we know that w is equal to 15 minus x. So our substitution for w is going to be 15 minus x. But we also know that area is equal to length times width. So if we actually do this, we know that the length is x, as given by the question. And due to our relationship between the perimeter and width, we know this has to be 15 minus x. So then if we wanted a formula that expresses the area purely as a function of x, we would do this multiplication and get 15x minus x squared. And that is based on us being able to create a substitution rule based on the fact that we know how much perimeter we have. I did 11, I did 12. Okay. So form a polynomial of degree 4 with the following zeros. So we know everywhere we have a 0, we can also write down an equivalent multiplicative expression. So for negative 4, we know that has to be related to x plus 4 equals 0. That's how we arrived at that solution. So in multiplicative sense, that becomes x plus 4 times x plus 2 times x minus 1 times x minus 1 equals 0. If we solve this, we would get -4, -2, +1, and +1 is our roots. But these could have unknown exponents. We don't know what power they're raised to. But the question tells us the polynomial only has degree 4. So if we wind up multiplying all this together, we have an x, an x, an x, and an x. So that by virtue alone already gives us an x to the 4th. So that is already a 4th degree polynomial. So all of these have to have exponent 1. Because if they had any higher exponent, our polynomial would not be degree 4, it would be some higher degree. So then it just comes down to actually doing this multiplication. So we have x squared plus 6x plus 8 times x squared minus 2x plus 1. Then we have x to the 4th minus 2x cubed plus x cubed squared plus 6x cubed minus 12x squared plus 6x plus 8x squared minus 16x plus 8. So then, if we wind up adding all of that together, we get x to the 4th plus 4x cubed minus 3x squared. No. Oh. Minus 10x plus 8. So that would be our final expression for a polynomial that has the listed zeros of degree 4. And question 14 we did. Question 15, find vertical asymptotes. So, for vertical asymptotes, you're looking for a fraction with a 0 denominator. Because every time you divide by 0, you're going to wind up with a vertical asymptote. So looking at this fraction, we're going to take the denominator and set it equal to 0. So we have x squared minus x minus 12 equal to 0. If we carry out that factorization, we get x plus 3 times x minus 4 equals 0. Solving each of those individually for 0, we get x is equal to -3 and x is equal to +4. Each of those represent a vertical asymptote. The function is not evaluatable at that point, and it approaches it asymptotically from both sides. For horizontal asymptotes, we want to first reorder your numerator and denominator in order of powers. So on the top we have 3x squared plus 11, so we're going to 3x cubed minus plus 11, so we're going to leave it like that. On the bottom, we're going to rearrange it slightly, so we have minus 2x cubed plus x squared. Now, when you're evaluating horizontal asymptotes, what you wind up doing is ignoring any of the lower powers in each of the expressions. So just find what the max is. Because as you get farther and farther away, like for example, if we're at x equals 1,000,000, if you look at x versus x squared versus x cubed is so much bigger than x squared and x that it becomes irrelevant. That this function is approximately equal to 3x cubed divided by negative 2x cubed. So now that we've isolated the highest powers in the numerator and denominator, we do any algebra that we can. In this case, we see that they cancel, and we wind up with an asymptote of negative 3/2. So looking very far away, either to the left or right in the x direction, our function approaches negative 1.5. Now, this only worked because we happen to have the top and bottom powers exactly equal. In situations where they're not equal, if the bottom is lower or the top is higher, you will have either vertical asymptotes instead, or oblique asymptotes, or no asymptotes at all. So you'd have to carefully evaluate it. For horizontal asymptotes, the power on the top has to match the power on the bottom. If it does, then you approach a horizontal asymptote. And this is an example of that, an oblique asymptote. So to calculate this, you'll actually have to do polynomial division. So you have an expression where the highest power in the top is an x squared, the highest power in the bottom is an x. For that, you can't just simply ignore all the other terms. You have to actually manually do the division. So we're going to do that. So we have 2x squared plus 3x plus 4 divided by x plus 5. So in the first term, we want to get to 2x squared from x. So we'd be multiplying by 2x. We do that, we get 2x squared plus 10x. And if we subtract that, we wind up with minus 7x plus 4. The 4 just gets brought down simply. And again, to match that, we're going to multiply by negative 7, which gives us negative 7x minus 35. So negative 7 minus minus 7x, that cancels. Whoops. And we're left with 39. So what that means is that we can rewrite this expression as 2x minus 7 plus 39 divided by x plus 5. So if we look at this for, let's say, x, again, we plug in 1,000,000. 39 divided by 1,000,000 is equivalently close to 0 compared to how big 2 times 1,000,000 is going to be. So we see in the long term, this function kind of behaves like 2x minus 7 for very large values of x. So that would be our oblique asymptote, the value that this function approaches as you go left or right, far away from the origin. And the only way to calculate that is to actually do polynomial division and find what terms are left over fractionally that you can eliminate in the long term. Uh, 18 we did. 19, or 18 and 19 the same?
I noticed that earlier. And I'm not aware of that. 18 was supposed to be that.
Whoops. Okay. So we're just going to call this question 18. And what we're really finding is the fourth root of x minus 2. So again, this is function composition. So just find the largest components you can. You see something weird is happening with the fourth root. So I'm going to call one of my components the fourth root of x. And then you have this interior stuff. So I'm just going to call that by itself. And if you put those two together, it allows you to form your resulting equation. So I'm going to call this g of x, since it's my outer function, and f of x is my inner function. So now I'm going to take this and replace it in g of x wherever I see an x. So here, there's only one x. So I'm going to replace that directly in, and I'm going to get the fourth root of x minus 2, which is, in fact, what we're looking for. What? Oh, yes, because you're doing f of g. True. So this should be f of x. This is g of x, because what you want to do is, yeah, because you want to plug g into f. When reading this, you're reading it backwards. G goes into f, not the other way around. I wonder if that's a mistake on the other one, too.
No, the other one was okay.
Yeah, okay. Did that, 21, we did. It's just creating same bases. Find the domain of the function. So that isn't bad. So for domain, ln, log, and root have fairly the same rules. To really do them, the insides need to be greater than or equal to 0. Or actually, in lin and log, these have to be strictly greater than 0. So what we're going to wind up doing is simply setting 10 minus 2x to greater than 0. If we move the 2 to the other side, we get 10 is greater than 2x. We get 5 is greater than x. So if we wanted to write our domain, x has to be less than 5. So we would say negative infinity to positive 5. Or in set notation, x, given that x is less than 5. Nope, so this one actually has a continuous domain. There are no breaks, there are no empty points, there are no piecewise components. It's just if you plug in a value less than 5, that works fine. If you plug in a value greater than 5, it gets all screwed up and you're done. So similar to square root. But square root, you can put 0 in a square root. You can't put 0 in a log, but you can't put negatives either. So it comes with similar rules. All right. You're welcome. So this, if we were going to solve this equation, what we're going to wind up doing is trying to isolate all our exponents on one side and numbers on the other. So I'm going to subtract 3 from both sides, and we're left with 6 ln of x is equal to 9. To further isolate that, I'm going to divide both sides by 6, which leaves me ln of x is equal to 3 over 2. Now, if we remember the rules of exponents, what this is saying is that if you have ln of a is equal to b, what you're really saying is that e to the b equals a. So what you want to do is rewrite this. We're not really doing calculations or algebra. This is simply rewriting it. So e to the 3/2 is equal to x. Okay, that might be our entire review for 1105, your final exam. Check the link, check the written descriptions. If you have any further questions, feel free to come in. We'll be more than happy to help.